Let's get right into it. Welcome to this explainer. Today, we're embarking on a journey of absolutely staggering proportions. We're talking about the sheer, awe-inspiring scale of how we take raw, reddish dirt straight from the earth and somehow transform it into one of the most highly engineered, crucial materials on our entire planet. It's a story of extreme heat, violent chemical reactions, and just incredible precision. So, I want you to keep this question in the back of your mind as we go through this. How exactly does red dirt become the backbone of modern skyscrapers? Steel is this ultimate symbol of strength, right? It's literally been the foundation of human civilization for over 4,000 years. What started way back with ancient blacksmiths in Anatolia has exploded into a massive multi-billion-dollar global industry today. But the core mystery is still there. How do we actually get from a pile of rocks to those sleek, towering structures we see in our cities? Okay, let's dive into this. Here is our roadmap. First, the blast furnace. 2, the pig iron problem. 3, primary steelmaking. 4, chemical purification. 5, secondary refining. And finally, number 6, continuous casting. Section 1. The blast furnace, the first massive crucible. Before we zoom all the way into the intense chemistry, let's just look at the big picture. Our story kicks off in a massive blast furnace. We're talking an imposing structure, often over 30 meters tall. The whole life cycle of our metal involves 4 overarching steps. First up, we actually mine the raw iron ore from the earth. Second, we do the iron making in that giant blast furnace. Third, and we're going to spend a ton of time on this one today, is the actual steel making and refining process. And finally, step 4 is casting and finishing that metal into a usable, solid form. So what exactly goes into that 30-meter tall furnace? Well, 3 main raw ingredients are fed right into the top. First, we've got iron ore, which is basically a reddish-brown rock packed with iron oxides. Second, we add coking coal. Now, this is coal that's been baked in airtight ovens for 12 to 16 hours, so it becomes this porous, high-carbon solid fuel. Crucially, this coke acts as both our fuel and our reducing agent. That means it's going to literally strip the oxygen atoms away from the iron ore. And third, we toss in limestone, which acts as a flux to absorb the waste materials and form a protective layer called slag. Once all those ingredients are inside, a continuous blast of superheated air is forced up from the very bottom. This combusts the coke and drives the temperature up to a staggering 2,000 degrees Celsius. To put that in perspective, that's roughly 3,600 degrees Fahrenheit. At that crazy temperature, we're creating this violent inferno that successfully melts the solid rock completely down into liquid iron. Section 2. The pig iron problem. Flaws of raw material. Now, you might be thinking, great, we melted the rock, we have our metal, we're done, right? Well, not quite. Here's where we hit a massive snack. The initial output from the furnace is something called pig iron. And the crucial point is, pig iron, or hot metal, has an incredibly high carbon content. Because of all that excess carbon, this metal is exceptionally brittle. It is completely unworkable for modern construction. Actually, if you were to let pig iron cool down and then hit it with a hammer, it could literally shatter into pieces. Not exactly what you want for a skyscraper. Let's zoom in microscopically for a second and look at the exact chemical breakdown. You can see exactly why pig iron is so flawed. It's got about 4 to 5% carbon, 1 to 1.5% silicon, and around 0.5% of manganese, plus a few other elements like phosphorus and sulfur. At this stage, these are all impurities. If we want to make high-quality, workable steel, every single one of these impurities has to be systematically purged. Section 3. Primary steelmaking, the chemical battlefield. This right here is the climax of our explainer. This is where iron truly becomes steel inside these towering converter vessels. Basically, there are 2 primary arenas where this chemical battle goes down. On one side, we have the basic oxygen furnace, or BOF, which uses a supersonic blast of pure oxygen to refine the molten pig iron. On the other side, we have the electric arc furnace, or EAF, which uses incredibly high-powered electricity to melt down 100% recycled scrap steel. While the EAF is absolutely crucial, especially for recycling, the basic oxygen furnace is actually responsible for up to 70% of the steel produced in the US today. So for the rest of our journey, we're going to focus intensely on exactly how this BOF operates. Section 4. Chemical purification, the oxygen showdown. Okay, let's dive deep into the inner workings of the basic oxygen furnace, which, by the way, was historically known as the Linz-Donowitz process. The BOF operates through this highly choreographed, unbelievably fast-paced sequence. First, a massive bucket charges solid scrap metal straight into the vessel to act as a much-needed coolant. Second, blistering hot molten pig iron from the blast furnace is poured directly on top of that scrap. Third, a water-cooled metal pipe, they call it a lance, is lowered deep into the belly of the furnace, hovering right above that liquid metal bath. And finally, the furnace unleashes a blast of 99% pure oxygen at about twice the speed of sound. It's wild. This whole sequence is so wildly efficient that it can convert up to 350 tons of iron into refined steel in less than 45 minutes. Now, what's really interesting here is the sheer microscopic violence happening inside that furnace. That supersonic oxygen penetrates deep into the bath, and at over 1600 degrees Celsius, those oxygen atoms aggressively bond with the excess carbon we're trying to get rid of. This reaction violently creates carbon monoxide and carbon dioxide gases. So the carbon is quite literally burned out of the molten metal. It bubbles right up and escapes the furnace entirely as an exhaust gas. But carbon isn't the only impurity we're fighting here. That high-speed oxygen is attacking the other elements too. The silicon oxidizes into silica, the manganese into manganese oxide, and the phosphorus into phosphorus pentoxide. But here is the real trick. These newly formed oxides, they're highly acidic. If we just left them alone, they'd stay right there in the metal. So we have to add a basic flux, specifically something like burnt lime or dolomite. The basic lime chemically binds with those acidic oxides to neutralize them. This creates a lighter, liquid layer of waste that floats right on top of the molten steel, which is known as slag.
Section 5. Secondary refining. The Master Chef's recipe.
And this brilliantly illustrates what happens next. Once that primary oxygen showdown is over, we carefully pour or tap the liquid steel out of the BOF into a giant bucket called a ladle. Just look at this massive drop in carbon. We started with pig iron sitting at around 4% carbon, making it uselessly brittle. But after our 45-minute supersonic oxygen blow, the carbon content in our refined steel has plummeted to a mere 0.05%. We've successfully stripped out that fatal flaw. But hold on, pure iron with just a tiny bit of carbon is really just a blank canvas. Secondary refining is where we get to play Master Chef. Operators can actually create over 1,500 highly specific steel chemistries by carefully injecting exact alloys into the molten bath. You want to increase strength and toughness? Throw in some manganese. Need extreme hardness? Drop in some chromium. Looking for corrosion resistance for, say, stainless applications? Mix in some nickel. Every single grade of steel is custom-tailored right here in the ladle.
The ladle furnace is also where we finally tackle our most stubborn enemy, sulfur. Sulfur is this pesky impurity that severely degrades the quality of steel. But here's the catch. The basic oxygen furnace cannot remove it. Why? Well, because sulfur requires a reducing chemical environment to be stripped away. And the BOF is fundamentally an oxygen-rich, oxidizing environment. So it's only here, in the highly controlled atmosphere of the ladle furnace, that we can add specific fluxes, like calcium oxide, to finally purge that residual sulfur.
And right before this perfectly seasoned metal can be cast, it goes through one final, honestly mesmerizing step: vacuum degassing. The entire ladle of glowing liquid steel is placed inside a sealed room, and a super powerful vacuum is drawn. During that intense oxidation phase we talked about earlier, gases like hydrogen, nitrogen, and oxygen get trapped inside the molten metal. If we were to just let the steel freeze with those gases still inside, they could cause microscopic cracks and defects later on. So the vacuum literally sucks those dissolved gases right out of the liquid.
Section 6. Continuous casting. Solidifying the foundation.
Okay, so we've successfully mined it, melted it, burned out the impurities, and perfectly tailored the chemistry. Now it's finally time to freeze this perfectly engineered liquid into a solid state. Historically, steel was poured into individual static molds to form ingots, which then had to be heavily reheated and rolled out. Honestly, it was a really slow, costly, and inefficient process. Today, the industry standard is continuous casting. Just like the name suggests, molten steel is poured into a water-cooled copper mold where it begins to freeze on the outside. It continually solidifies and gets pulled downward into virtually endless slabs. It is an absolute marvel of modern efficiency.
Let's follow this continuous flow for a second. First, the ladle empties its 3,000-degree molten payload into a reservoir funnel called the tundish. The tundish smoothly feeds the liquid metal down into the water-cooled mold. As the metal is pulled vertically down through the caster, it freezes, exiting as massive, red-hot slabs that can be up to 40 feet long. From there, it heads right to the hot strip mill to be rolled out into thin sheets. And incredibly, this entire sequence is entirely automated. It's completely untouched by human hands.
So think back to where we started. We started with literal piles of red rock, baked coal, and limestone. And through a staggering gauntlet of 3,600-degree heat, supersonic oxygen blasts, and incredibly delicate vacuum chemistry, we've created the foundational building block of modern society. From the ancient blacksmiths of Anatolia to a highly automated multi-billion-dollar global industry, steel has pushed the very limits of human engineering. It really makes you wonder, with all the wild advancements we are making today, what will the next 4,000 years of steel innovation build? Thank you so much for joining me on this explainer. I really hope you found this journey as absolutely fascinating as I do.